Hello. So we are moving on to lesson 4.4, exponential and log equations here. So we're going to start with solving exponential equations by expressing each side as a power of the same base. So if we have b to the power of m equals b to the power of n, then we know that m equals n, right? Because the bases are the same. So we can rewrite the equation in the form b to the power of m equals b to the power of n. Again, bases are same when we do this. Then we're going to set m to equal n, and then we'll solve for the variable. So those are the three steps that we're going to be doing. So let's look at an example using this technique. Um, so a, 5 to the power of 3 to the 5 to the power of 3 times x minus 6 equals 125. So what we're going to do here is we need both sides with the same base. Well, 125 can be written as 5 to the power of 3, right? It's the same thing as 125. So now the bases are the same, and we can just take the exponents. So 3x minus 6 equals 3. And now we're going to solve. We're adding 6 to both sides, so we get 3x equals 9, and dividing by 3, we get x equals 3. Now, before we say that this is the answer, we're going to go ahead and check, and you are checking it in with the original equation, not the one where you already have the same basis. So we're going to do 5 to the power of 3 times 3 minus 6. This should equal 125. Well, when we do 3 times 3 is 9. 9 minus 6 is 3. And we know that that equals 125. So this is true. So we know that our solution set for this is 3. Okay, let's look at the next one here. So we have 8 to the power of x plus 2 equals 4 to the power of x minus 3. All right, so again, we need the same powers, or not, sorry, the same bases, of course. Well, we can't make so that, 8 becomes a base 4, so we're going to have to go even further down, and both can be written as base 2, right? 4 is 2 to the power of 2, and then we still have x minus 3 over here. 8 with base 2 is the same thing as to the power of 3, and we need the x plus 2 um, still in the exponent because that was in the original exponent. So 8 and 2 cubed, and then we have our 4 and 2 squared. Okay, now our exponents are the same, or sorry, I keep messing up that word. Our bases are the same, both are with base 2. So what we can do is we can just take the exponents. 3 times x plus 2 equals 2 times x minus 3, right? We're going to distribute, so we get 3x plus 6 and 2x minus 6. Now I'm going to subtract 6 from both sides so that I'm actually moving it to the right. 3x equals 2x minus 12. I'm subtracting 2x from both sides so that I can move the x's. So x equals negative 12. And again, I'd recommend checking to make sure that it is correct. So our solution set is negative 12. Solution set is always inside parentheses. Okay, next we're going to use logs to solve exponential equations. So First, we're going to isolate the exponential expression. Second, we're going to take the common log on both sides of the equation for base 10. Take the natural log on both sides of the equation for bases other than 10. And then we're going to simplify using one of the following properties. So we have natural log of b to the power of x, where this is the power rule, or natural log of e to the power of x, which we know that this does equal 1. So our answer is going to be x, because it's going to end up with x times 1. Or if we have the common log, 10 to the power of x, again, we know that this equals 1, so this is going to be just x. And our first step is to solve for the variable. Okay, so let's look at an example here. We have 5 to the power of x equals 135. Our first step is to isolate the exponential expression. Well, that's already done here. Second step is to take the common log on both sides of the equation for base 10. Or take the natural log on both sides for the equation for bases other than 10. Our base is other than 10, so we're going to take the natural log of both sides right here. Now we're going to bring the x to the front, and then we are solving for x, so we are dividing by natural log of 5, and we get x equals natural log of 134 divided by natural log of 5. When we do this calculation, we get 3.04. So this is an approximated value. It is a rounded number, 3.04. So our answer, to give it as an accurate, would be the natural log of 135 divided by natural log of 5 and the braces, because it is a set. So unless you're given like, okay, round the decimal to the nearest 2 or 1 decimals, or if it says that round the decimal to the tenths or hundredths, you will give the answer as an accurate. So it'll prompt you to round it if you're expected to answer with a decimal. Okay, next example here. Again, we have the exponential expression already isolated. Now our base is 10, so we're going to use the common log. We're taking the common log of both sides. Oops, that's not an 8, that's an x, sorry. And then we bring the x over here to the front, and we divide. Well, here's the thing though. We know that this equals 1, right? So we're going to get, if we divide by 1, we're still going to get log of 8,000. And if we plug the common log of 8,000 into the calculator, we get 3.90. So this is the more accurate answer. So our answer is going to be common log of 8,000 with the braces. Okay, let's look at this next one. So we have 3 to the power of 2x minus 1 equals 7 to the power of x plus 1. Our bases are 3 and 7. So what we're going to do is we're going to take the natural log here of both sides. We are bringing the exponent to the front. So 2x minus 1 natural log of 3 equals x plus 1 natural log of 7. We're going to distribute, so get rid of the parentheses. So we get 2x natural log of 3 minus natural log of 3. Same thing here, distributing x natural log of 7 plus natural log of 7. Okay, next thing what we want to do here is we want to move the x's to the left and everything else to the right. So I want to move this natural log of 3 to the right, so I'm going to add that. Then I'm subtracting the x natural log of 7 because we want to move x's to the left. So these cancel out, these cancel out. So we end up with 2x natural log of 3 minus x natural log of 7 equals natural log of 7 plus natural log of 3. Okay, so we have moved all the terms with x's to the left. Now what we need to do is we need to take the x out from each one because it is a common factor on the left. So when we take the x out, we end up with 2 times natural log of 3 minus natural log of 7. And on the right, we don't have any common factors, so we're going to leave it like that. Now we can divide both sides by the 2 natural log of 3 minus natural log of 7, like this. And we get x equals natural log of 7 plus natural log of 3 divided by 2 times natural log of 3 minus natural log of 7. And that is going to be our answer for this one again. Yes, it looks complicated, but there's nothing else we can do. If we plug it in the calculator, it'll be again a decimal number. Okay, next what we're going to use is the definition of log to solve log equations. So step 1 is to express the equation in the form log with base b of m equals c. Then we're going to use the definition of a log to rewrite the equation in exponential form. So if we have log with base b of m equals c, we know that the base is the base for the exponential. Remember, the answer is the exponent c, and then m is the answer to the exponential form. Step number 3 is solve for the variable, and step number 4 is check proposed solutions in the original equation. So include in the solution set only values for which m is greater than 0. Okay, so we're going to go ahead and solve log equations. Now, this is our log. So log with base 2 of x minus 4 equals 3. What we're going to do is we're going to do the first step here. So, and actually, no, never mind. That is already done. I meant we're going to do the step 2. So we're going to rewrite it as the exponential form. Our base is the 2, exponent is 3, and this equals x minus 4. So 2 cubed is 8. We add 4 to both sides, and we get x equals 12, or 12 equals x. We check in the original, so log base 2, 12 minus 4 equals 3. 12 minus 4 is 8. Now our base is 2, exponent is 3, that is 8, so this is true. So we know that our answer is going to be 12 for this one. Okay, same thing over here. We have 4 times natural log of 3x equals 8. What we're going to do here is we need to, again, isolate the log. So we're going to go ahead and divide by 4. So we get natural log of 3x equals 2. Our base is e, the natural base. Now 3x should be inside parentheses. Our base is e. E to the power of 2 equals 3x. Now, we need to divide by 3 to solve for x. So we get x equals e squared divided by 3. And we need to check in the original equation. So 4 times natural log of 3 times e squared divided by 3 equals 8. 3's cancel each other out. So we end up with 4 natural log of e squared equals 8. Well, we bring the 2 to the front, our power rule, and 2 times 4 is 8. And we know that this here is a 1. So 8 equals 8 is true. So our answer is e squared over 3. Next one. Um, this one, we're going to start a little bit differently. We need a single log on one side. Now we have an addition, but look, we have the same basis here. It's a common log for both. So what we can actually use here is we can use the product rule to combine these. So it is common log of x times x minus 3. X and x minus 3 equals 1. Now we're going to write it in as the exponential form. Common log, the base is 10. 10 to the power of 1 equals x times x minus 3. We distribute x squared minus 3x equals 10. Oh, fun times. We're going to subtract the 10 from both sides. So I'm going to flip it over so that I have x squared minus 3x minus 10 equals 0. Well, we need to factor next. So we are factoring this. It factors to x minus 5 and x plus 2 equals 0. So x minus 5 equals 0, which means that x equals 5, or x plus 2 equals 0, which means that x equals negative 2. Now, if we look at these numbers, we need to make sure that we can actually use them. X equals 5 is okay. We can plug in x equals 5 and everything looks fine. Of course, we should check that it works. X equals negative 2, there is an issue. We cannot have a negative. So common log of negative 2 is not possible. So we need to cross this one out and say that that is not correct. So we know that our uh, answer is going to be 5. And again, make sure that you check. Okay, using one-to-one property of logs to solve logarithmic equations. Remember that one-to-one property means that both um, the equation or the function and the inverse is a function. So both are functions. So one-to-one was where both the vertical and the horizontal line tests work. So we only have one input and one output. So step 1 is express the equation in the form log with base b equals m, or of m equals log with base b of n. So this form involves a single log whose coefficient is 1 on each side of the equation. Then we're going to use the one-to-one property to rewrite the equation without logs. So if, and the one-to-one for the logs was, if we have the same basis, then m equals n. Third step is to solve for the variable, and fourth step is to check proposed solutions in the original equation. So including the solution set only values for which, oops, m is greater than 0 and n is greater than 0. Like we saw in our previous example, we can't have less than 0. So they have to be greater than 0. So this is kind of the what we're using here, the basic one-to-one property of logs. Okay, so we're going to go ahead and solve this log equation right here. What we're going to use first is we're going to use the quotient property right here. Both are the same base. So actually quotient rule, not, well, yeah, quotient rule right here. Both are the same base and we have a subtraction, so we can rewrite it as a quotient. So natural log of 7x minus 23 divided by x plus 1. Now, we can use the one-to-one property because we have the same basis. So we can actually just write x minus 3 equals 7x minus 23 divided by x plus 1. Well, in order for us to go anywhere from here, we need to multiply both sides by x plus 1. These cancel each other out. And this one we're going to FOIL. So x squared minus 3x plus x minus 3 equals 7x minus 23. Now we're going to start moving things over and combining the like terms. So x squared minus 2x minus 3 equals 7x minus 23. We subtract 7x and add 23. To cancel these, we subtract 7x and add 23 here. X squared minus 9x plus 20 equals 0. Factoring comes in handy again. So to factor this quadratic equation, we have x minus 5 and x minus 4 equals 0. So x minus 5 is 0, or x minus 4 equals 0, x equals 5, or x equals 4. We need to check that both of these work. And again, when we're checking it in the original equation. So plugging it in where the original is. We're going to start with x equals 4. So natural log of 4 minus 3 equals natural log of 7 times 4 minus 23 minus natural log of 4 plus 1. And I don't, okay, ran out of page. Natural log of 4 plus 1. So natural log of 1, natural log of 28 minus 23 is a 5 minus natural log of 5. Well, look at that. Natural log of 1, well, natural log of, these are the same bases and we have a subtraction, so we can use the quotient rule again. 5 over 5. 5 divided by 5 is a 1, so this is all correct. So this is true. So 4 is an answer. Well, then we're going to go ahead and do it with the same thing with the 5. And check exactly like we did here, and it is going to be true. So we're going to have our solution set is going to be 4, 5. Both are answers to our equation. Okay, next one, we're going to look at an actual example. So how long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? So what do we know? The compound interest formula was given, and it looks like this. So our P is $1,000. Our A is $3,600. R is 8%, which is 0.08. And we are compounding quarterly, which means that we're compounding 4 times a year. Now, the question is how long? Okay, so let's plug in the numbers. 3600 equals 1000. 1 plus zero point zero 0.08 divided by 4 to the power of 4t. Okay, we need to isolate the exponential form right here. So we're dividing by 1000. So we get 3.6 equals, this right here is going to be 1.02 to the power of 4t. Since we have the t in the exponent, we're going to take the natural log of both sides. Now we can bring the 4 times the t to the front with the power rule. So 4t natural log of 102, natural log of 3.6, and that's a t. Now we divide by 4 natural log of 102 both sides. So we get t equals natural log of 3.6 divided by 4 times natural log of 1.02. When we plug this in the calculator, we get 16.2 years and to the nearest tenth of a year. Okay, a second application here. So the percentage of adult height attained by a girl who is X years old can be modeled by f of x equals 62 plus 35 common log of x minus 4, where x represents the girl's age from 5 to 15, and f of x represents the percentage of adult height. At what age has a girl attained 97% of her adult height? So 97 goes where the f of x is, and we are solving for the x, so for the age. We are subtracting 62 from both sides. So we get 35 equals 35 log, common log of x minus 4. We divide by 35. We get 1 equals common log of x minus 4. Now we're going to write it in exponential form. Our base is 10. So 10 to the power of 1 equals x minus 4. So 10 equals x minus 4, x. We move the 4, so we add 4 to both sides, x equals 14. So at age 14, a girl has attained 97% of her adult height. So percentage, um, yeah, so what I was going to say is that normally, like in the compound interest example, we converted the percent to decimals. But this right here says f of x represents a percentage of her adult height. That is why we're using the 97 percent here, because it says it right there instead of converting it to a decimal like we often do. Okay, that's it for this lesson. Let me know if you've got any questions. Bye.